Hey, chemistry. It's good to see you back. It's Thursday, the 2nd of April. I'd like for you to turn to page 404. At the bottom, you'll see a table 3. I forgot to mention table 3, and you had to use it to solve some of your problems, but every homework, every quiz is open book, open notes, and you know that. Okay, so look at table 3, page 404. Solutions are homogeneous, colloids and suspensions are heterogeneous. Next line. Particle size for solutions. Particle size is less than 1 nanometer. A nanometer is a billionth of a meter. Imagine this is a millimeter right here. That teeny tiny little space is a millimeter. Right there between my fingers. Well, that's a thousandth of a meter. A meter is if you put a million lines in that little teeny space. So that's pretty small. That's why solutions, so you say they dissolve solutes. Anyway, colloids, the particle size is between 1 nanometer and 1,000 nanometers, and suspensions are bigger than 1,000. And solutions do not separate on standing, and neither do colloids, but suspensions do. They settle out. Solutions cannot be separated by filtration, neither can colloids, but suspensions sure can. You pour them through a filter and boom, it catches all of the muddy water, the mud of the water. The water goes through. Solutions do not scatter light, but colloids do scatter light, and suspensions are so packed like mud that they will not allow the light through. So they're mostly opaque, not transparent. Okay, the next thing on page 405. Read with me that first sentence. Substances that dissolve in water are classified according to whether or not they yield molecules or ions. And so I'm going to show you what an electrolyte is. A substance that dissolves in water to give a solution that conducts electric current is called an electrolyte. So here's what we've got. When we have, let's say, an acid, a base, or a salt, electrolytes in solution come from acids, bases, or salts. All right, so an acid, hydrochloric acid. I got that down here. It's called muriatic acid at Lowe's. And it is formula HCl. When you take hydrogen chloride gas and put it in water, it forms, you see this? That detaches, combines with that. It forms hydronium ions. And what's left behind is chloride ions. You see, this is +1, and that's -1. When you bust it up, the plus goes with this and attaches it. It's just a proton. It's a hydrogen ion. And then what's left behind is a chloride ion. Bases would be something like sodium hydroxide. And you go ahead and put that in water, and it gives you sodium ions and hydroxide ions. And the reason is because water is polar. It has a positive end and a negative end, and we've already discussed that. And it comes up against this ionic compound, which is positive on one side and negative on the other. And so the positive side of this is attracted to the negative side of that, and it detaches the hydroxide ions. And another water molecule comes over and it gangs up on it like this, where the negative side is attracted to that and it pulls it apart. Water is electrically sticky, is what I say. That's just my terminology. Now, salts. Let me go a little deeper here. Salts go like this. You got sodium chloride, that's table salt. You put it in water, and it breaks it into sodium ions and chloride ions. And that's, once again, because the water is polar, it pulls that ionic compound apart. But when you take sugar, it's a non-electrolyte. Because it does not form ions in solution. You take table sugar, C12H22O11, and you go ahead and stick it in water, that's a solid, and you stick it in water, H2O, and it's going to become C12H22O11. Except now it's dissolved in the water, so we say it's aqueous. Agua, water, you know that. And so that's the way it works. The water just dissolves it. It breaks a big old chunk of sugar. Here's a chunk of sugar. And it breaks it down into crystals of sugar. When it gets all the way down to one molecule of sugar, it cannot separate the atoms in that sugar molecule because those covalent bonds are too strong. So even though the water is polar, it cannot polar apart the molecules. But it can pull apart ionic bonds because it's electricity with electricity. But this is not. This is electricity with covalent bonding, sharing bonding. Remember, we discussed that before. Non-metal with non-metal with non-metal. Okay, and another non-electrolyte is oil. And another non-electrolyte is, alcohol. Alcohol dissolves in water. It's said to be soluble or miscible, but it doesn't form ions. So it is a non-electrolyte. Now, what do ions, the formation of ions, have to do with carrying current of electricity? Well, what is electricity? Isn't it a flow of electrons? And so if electricity is simply a flow of electrons, does it get repelled from the chloride ions and attracted to the positive ions? Does it get repelled from the negative ions and attracted to the positive ions? And so it zigzags its way through the solution because of these electrolytes that are in solution. We say that all those electrolytes, these positive ions, are aqueous, and these negative ions are aqueous because they're in water. And so they're dissolved in the water, the electricity comes, they're repelled, attracted, and it works its way through the solution. We have a way of testing to see whether or not something's an electrolyte by using this little device here. Now this device has two electrodes. In fact, if I were to cross them with a metal, like if I had a screwdriver right now, I could go ahead and cross those things and the light would come on because I'm completing the circuit. The electrical circuit is plugged into the wall. And so that light will come on whenever there's an electric current. Will milk form an electrolyte? Ooh, they call it lactic acid, don't they? And so let's go ahead and see if acids form electrolytes in solution. There we go. There it is. You've also got this other kind of a tester. It's called a conductivity tester, where you're just simply testing to see if it will conduct electricity. So whether you check it to see if it's an electrolyte tester or a conductivity tester, they mean the same thing. Look at that light. Did you see that light come on? Let me see it again. You got that? Sometimes the electrolyte is so strong that it flashes rapidly on this little tester. And that means it's a strong electrolyte. Okay, let's go ahead and check orange juice. Isn't orange juice citric acid? Boom. Yeah, it is. Let's check it on here. See if there's ions in solution with this little tester. Yep. Do it again. Yep. Okay. Now we're going to go ahead and check a vinegar. Of course, you know vinegar is acetic acid. Now, what's interesting about vinegar, it'll show us an electrolyte. Yes, it will. But let's take vinegar that doesn't have any water. You know this package has 5% acetic acid in it, and it's 95% water. So you're really getting gypped, I suppose. But if you take all the water out of acetic acid, you'll have glacial acetic acid, it's called. And it's almost 99.8% acid, hardly any water at all. Whew, really opens your nostrils. And I'm going to go ahead and I'm going to put a little of this glacial acetic acid down here and check it. And you'll see the light does not come on. However, if I water it down like that is, I'm going to take some water, I'm going to put it in there. See? See? So it becomes a better electrolyte if you add the water. So this thing here is a non-electrolyte, but when you water it down, it becomes an electrolyte. Now let's take a look at just plain old distilled water. Nothing. So take a look at it on my little more sensitive tester. Ooh, that's because, you know, I needed to clean these off between use. That's the problem. Now let's go ahead and take, well, maybe I didn't clean these up well enough. Go ahead and check it now. Nothing. Try it again. Nothing. Okay, but now let's take regular tap water, which has chlorine in it. Of course, you guys know that. They put bleach in the water just to clean it up for you, so when you drink it, you don't get all those nasty things. Here it comes. Boom, do you see that light? Let's try it again. Boom, boom. And let's go ahead and check it with this thing. Here we go. So that chlorine makes it into an electrolyte. Oh, you can't see it with this light bulb. It's not as sensitive as this thing is. Okay, so that's a better electrolyte tester. And I can check these other things too. Ammonia is considered to be basic, so it's an electrolyte. Alcohol is a non-electrolyte. Let me show you that. And I'm running on about 13 minutes right now. Got to get on with it. Oh, right, there we go. Non-electrolyte, alcohol. Now, well, let's turn the page. I'm over to page 406. What's a non-electrolyte on page 406? It's a substance that dissolves in water to give a solution that does not conduct an electric current. And I've shown you all the demonstrations. Page 407. There are 3 ways that you can affect the rate of dissolution. You know, dissolution means dissolving. So how do you make sugar dissolve more rapidly? Well, you just crush it up. That's one thing, increase the surface area. I have a mortar and pestle. I grind on it and it makes it powdery and it'll dissolve things more quickly. In other words, you give more surface area to the solvent. Solvent water has more, I like to think of water as like piranha that are attacking the solute that's going in. So the sugar going in is being attacked by the water, which is polar, and it's basically pulling the thing apart. And if you have more surface area for that water to get to, it's going to dissolve more rapidly. Agitating the solution, not crushing it up, but stirring it up, helps to dissolve more rapidly. And the third thing, heating the solvent. And I'm on page 408. Heating up the solvent will cause the particles of water, the molecules, to move more aggressively. And because they'll have more kinetic energy, the temperature is higher. And so they will start attacking the invader, the solute, more, and it'll heat it up. So down here at the bottom of page 408, you see a system that is saturated. A system that is saturated, how do I know that it's saturated? Well, let's just take a look here. Let's put some sugar in this here beaker, and let's go ahead and add some water. Let's agitate the solution by stirring it up. And if all those little crystals go away, which they have, they've all gone away, you can look at the bottom. You can look at the bottom, there's nothing down there, then you can go ahead and say that it's unsaturated. When it's unsaturated, it can hold some more. But when you put so much crystal, see, because between the water molecules, there are spaces. And when you break this salt up into these sodium and chloride ions, they fit in between those spaces between the water molecules. But there comes a point when their spaces are all filled up. That's called saturated. And so when I pour as much more than this thing will hold, and it's based upon the temperature of the solvent and the amount of solvent. So there's only so much that this little bit of water will hold. And if you look, you're going to see that there is a line down there. Whoop, there's an amount down there that hasn't dissolved. And it won't dissolve because it's too much for that little bit of water. It'd be called, we have said, it is saturated. It holds everything that it can hold if you can see flakes on the bottom. It's either unsaturated, saturated, or supersaturated. We'll talk about supersaturated solutions tomorrow. No matter how much I agitate this, it won't go into solution because all those little spaces between the water molecules are filled up. It is saturated. So I'm going to read those definitions and quit. What is a saturated solution? It's a solution that contains the maximum amount of dissolved solute. What's an unsaturated? It's a solution that contains less solute than a saturated solution under the same conditions of temperature and pressure. And look at over here to the left on 408. 408, solution equilibrium. Well, when this thing is saturated, the question is, are there still some grains of salt that are getting together because they have positive and negative attraction? And so those formula units, I should say, those formula units are clumping together and falling to the bottom. At the same time, there's some of the extra material on the bottom that is redissolving into those spaces. And so it's going like this. It's decomposing and dissolving. It's coming back together and it's pulling apart. It's coming back together and it's pulling apart. It's coming back together and it's doing that constantly. And so there's an equilibrium. And the rate at which it dissolves is equal to the rate it recrystallizes is the rate at which it dissolves. And that's only for saturated solutions called equilibrium. All right, we'll talk about supersaturated solutions tomorrow. And I might do a little different way of giving quizzes from now on. I might just put a PDF file on there and have the questions and then have the bare bones quiz next to it. You'll figure it out. I'll just write you some instructions. But then on the other hand, I might type all those questions in again myself. See ya.